Hi everyone, we are back and we are about to go through our lecture 6, chi-square distribution and goodness of fit tests, goodness of fit hypothesis testing. So we've discussed Gaussian normal distributions, t-distributions, other distributions. One of the other distributions we're going to encounter now and a little bit later on in this course is the chi-square distribution. So it's distinct because as we can see below here, it kind of has this right tail, right skew. So it is not, and I repeat, it is not symmetric. The area of the curve is 1, but again, and as nu becomes large, it will approach Gaussian or normal distribution, but it is not. So that is going to limit some of the test and change some of the kind of the critical values that we're looking for here. So chi-squared is basically our goodness of fit test statistic. It is defined as such. So it's the sum of the observed minus the expected, and I is indicating over k, where k is essentially the total number of variables being compared, or, you know, and that's a very, very good definition. I'm going to kind of talk about the number of outcomes as well. Additionally, nu is equal to k minus 1 minus r, where r is the number of fitting parameters, and more on that a little bit later. So k is not your number of samples. So k does not equal n necessarily. That is very, very important to remember. So the chi-square test is going to be a right-tailed test for hypothesis testing. And it's since chi-square is a positive value, always, as you can see here. And basically, we'll see the observed data. When the observed data approaches the expected, the chi-square approaches 0. So makes sense. You're looking at those differences. So why don't we go ahead and we can actually do a quick, a quick problem to kind of illustrate this. So I'm flipping a coin 500 times. So my outcomes, if I'm flipping a coins, are heads or tails. So already k is equal to 2 here. So if I'm looking at heads and tails, and I look at my observed over the expected, if I do it 500 times, if it's a true coin, I would expect 250 heads, 250 tails, because they're equally probable. But I find, or my student finds, 286 heads and 214 tails. Is this coin fair or true using a confidence level of 95%? Well, we're going to run through the same kind of idea that we ran through previously in terms of our hypothesis testing protocol. Here, we're just looking, are they observed or are they expected? R is basically looking at fitting parameters. So are there fitting parameters that we're asked to compare against here? And that R is effectively 0 here. We'll see another problem where we're asked to see, or if there's additional variables that we have to account for in our nu degrees of freedom. Because remember, nu is going to be equal k minus 1 minus r. R is additional fitting parameters that eliminate degrees of freedom, 0 here. So our nu here is just 1. So let's do our hypothesis testing protocol. Our null frequencies are the same, meaning observed matches expected. Alternative, they're different. What's our confidence percent? 95%. And now we need to calculate our chi-squared experimental. So we can kind of do that fairly straightforward in R. So let's pull up R. Let's create a whole new little folder here. But I want to bring in my library, tidyverse, library, stats, library, R, statics. Let's do ggplot. Bring that in. All right, so let's go ahead, and I could just do, I'm going to sum this. So this one's 286 observed minus expected square divided by 250 plus, was it 214? 214. 214 minus 250 squared divided by 250. And we get a value here of about 10.368. Let's check if that is correct. 10.368. Good, that's our experimental. It is a right-tailed test. So remember, if we're remembering kind of back to our old, this is the do not reject, this is the reject region. So this value is, let's see, our experimental actually. We need to figure out what is our chi-squared theoretical. So it's a 95% confidence interval. So our chi-squared also has an alpha and a nu. It's never going to be over 2. So our chi-squared is 0.05. Our nu is 1. We could look at our chi-squared table below here. Hopefully. There's our chi-squared. So 0.05, 1, so it's 3.841. And we see that that is indeed our value here. So 3.841, that falls, if this is 3.841, our experimental falls in that reject region. Excellent. But we've got another way to test, and let's go ahead and introduce that now. So we can actually, let's create a list. Let's call this observed, and then we'll say observed was list, if we had 286, let's make sure we have this consistent. Observed, predicted, 250, 250, good. And then now I can do chi-square test, where I'm going to set x equal to observed and p, equal to predicted. And oops. So for predicted, we actually it's a good error to see. They have to sum to be equal to 1, so I have to basically divide this by 500. So a half. So here, and we can see what our values were obtained. So I see I have a degree of freedom of 1, which is great. Chi-squared value of 10.368, good. And now here, this is why we spent that time on that p-value analysis. So 0.001, that is much less, right, than our 0.05 value. So it falls in the reject region. Got it. So this is the same test, and again, you can kind of do it both ways with R, not an R, but again, the interpretation is really critical here. So excellent. Next time we'll move on to a couple more examples, and then we'll get going. Thanks. See you next time. Bye.